two charges. Okay, let's say this is plus q. Okay, and then there is another charge minus of 3q. Okay, understand this question. Understanding is important. After that, we can solve it. And let's say they are separated by a distance a. Okay, they are separated by a distance a. So that's fine. Okay, so the question is, you have to find where v is equal to 0, where the potential would be 0. Okay, on the line joining the two charges. So if you join two lines, 2 points, obviously you're going to get a straight line joining two charges. That's the question. Okay, so it has got a very interesting approach to it. The first thing is, this is minus q, this is plus q. So the potential will be zero. You mean, whenever we are saying potential, and since it's a scalar quantity, we'll include the sign. But whenever we are talking about an electric field, because of the positive and the negative, we consider the direction. Okay, so that's the basic difference that is very important. So let's say the potential is zero at this point, let's say at a certain point, and let's say that particular point is at a distance, let's say x from plus q. Okay, and that means from minus q the distance would be obviously a minus x. Can't be exactly at the center because the magnitude is different here, and potential is inversely proportional to distance. So more the distance, less would be the potential. This is already a low charge. So whatever is the potential, if it has to be zero, it has to be closer to this q. Okay. Let's say this point is x. So now I think we can, find it out. If we check the potential difference at this particular point, okay, we can find out. Okay, or rather we can say that what is the total potential at this particular point. So potential is a vector quantity. If you want to find out the potential, you can use superposition principle. You can add the potential because of this plus because of this. So let's see what is the potential at this because of plus q. That is obviously nothing but kq divided by x, the distance from the charge. That's this. Plus, what is the potential at this because of minus 3q. So as I said, it's a scalar. We have to consider the minus sign. So I can write it down as minus of 3q divided by a minus x. And of course, k is there, kq. So k into 3q, right? But as we said, we have to find out where the potential is 0. This must be equal to 0. And this way, we can easily find out the answer. So if I just write it as kq divided by x is equal to 3kq divided by a minus x. So this kq and this kq will get cancelled. It is 0. I'm taking it on the other side, simplifying things. Do the cross multiplication. This is 3x is equal to a minus x. So I have to find out what is x, because x is the unknown. I know the distance between the two charges is a, so I can find out x in terms of a. So 3x goes on this side, this would be 4x is equal to a. That means x is equal to a by 4. Okay, so you can put the value of x as a by 4 here. This also a by 4. Do the calculation, you will see that your answer will become 0. That's obvious, right? So this is the answer. But then this is not complete because it can have two answers to it. This is one position. Another position can be outside. Another position for this may be here. Okay, somewhere outside, because the potential because of this positive will be there, but the potential because of negative will also be there. And if they are opposite to each other, they will try to cancel out each other and become v is equal to 0. It cannot be on this side because this is a larger charge. So this is going to implement more potential. This is a smaller charge. The potential distance is also large. So what happens, the potential because of this would be very small here. This would be very large. So this side it can never be negative. But the potential of this side would be small for this, but it will be slightly large for this. So that means I can have a point here where maybe the potential will be again 0. Let's say this particular point is y. This is at a distance y. So we can also do this calculation. Okay, so let's find out this now. So the potential at y is nothing but k q positive divided by the distance between this positive charge and this point is y. We have written, let me write it down as y, then minus 3kq divided by, this time it's y plus a, y plus a, that's the distance, right? So we can write it down as y plus a. This time it should be again 0. So if you do our calculations here, this would be kq divided by y is equal to 3 times kq divided by y plus a. Again kq gets cancelled, and this would be 3y is equal to y plus a. Same thing, 3y minus y is 2y is equal to a, means a is equal to, or sorry, y we are finding out, y is a by, so this distance is at a distance a by 2. So there also the potential would be 0. So many a times we might leave halfway. We might think that this would be the answer, but no, you have to use some logic and understand that the chances are there that on the other side also the potential may be 0. So that's important. Okay, so so now we are going to find out the potential. Okay, we're going to do two things here so that we get the concept of potential as well as electric field. Potential is a scalar and electric field is a vector, and electric field at P, at let's say at point P, due to a charged ring. This is interesting. Okay, due to a charged ring. Okay, we're going to write down the concepts first, the important things that we should actually know due to a charged ring. Okay, now what happens here is that if you're basically finding out the potential, it's a scalar quantity, and in electric field it's a vector quantity. And if we just try to recall our formula for both these cases, we have got potential is kq by r, and electric field is kq by r square. Please remember, very important, that these formulas are valid for point charge. We have one charge at certain point and we are doing it. Okay, so we are having this validity for point charge, but we are going to use this formula, we are going to use a trick so that we are able to find it for the ring as well. So we have got a charged ring. So let me just draw a ring here. This is my charged ring. Okay, let me just find out the potential first. Let's talk about the electric field later. We are going to calculate potential now. So we've got a charged ring. So charged ring means positive ring, let's say. By positive and negative, I think it's quite clear. Only the direction will change. In case of electric field, potential we can measure. And we want to find out what is the potential at a particular point P. Okay. And let's say that particular point P is at a distance x from the center of the ring. Okay. Imagine this is a three-dimensional picture, and this is the radius of the ring, which is capital R. Okay, and let's say we are considering a very small point here, a very small point. Okay, and this particular point has got a charge dq. So this dq is a very small charge in a very small point, so that means this dq can be considered as the point charge. Okay, so if you want to find out what is the distance between point P and the point charge, we can use our Pythagoras theorem, and this would be nothing but root over of r square plus x square. Now this is the entire scenario. We're going to find out the potential now. Okay, so if we want to find out what is the potential, okay, potential at P due to dq, we can use this point charge formula. Okay, due to dq is like a point charge now. Okay, like point charge. So let's use our formula now. So that means whatever potential we are going to have here is a very small potential. So let me write it down as dv because it's because of a small charge. So it is k dq divided by r. Okay, so I can simply write it down as k dq. R means the distance. So this is my r, the distance between the point and the charge. So we have seen in terms of the known quantity, it is nothing but root over of r square plus x square. Okay, so that's my factor here. Okay, now if I want to find out the total potential, so maybe I can find out the total potential, v total. So what we can do here is I can divide this into small spaces, dq, 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 all will be dq. Okay, and then what I'm going to do is I'm going to add them up. But we know if it is continuous, we don't use addition, we use integration. So that means if I want to find out the total, this would be integration of dv, which is nothing but v total, which is integration of k dq by root over r square plus x square. What we should note here is that this distance r square by x square, is it a variable or a constant? The answer is it's a constant, because you see, if you look it from a three-dimensional point of view, okay, a bit difficult to show you on screen, but imagine it from a three-dimensional point of view. It's a ring. Okay, it's a ring, and the point is p is just at a distance x from the center of the ring. So if you see that this ring is coming out of the board, point P is here, you take any point from the ring to the point P, the distance will more or less remain the same. It will always be root over r square plus x square, because P lies along the axis, along the center of the ring, and the ring is surrounding it and making an angle 90 degree. Okay, so whether you take this distance from the center, wherever, the distance will always remain root over r square by x square from whichever point you take around the surface. Okay, three-dimensional picture. So this means this particular distance that we have is k divided by root over r square plus x square. Okay, integration of dq. So dq is a small charge. Let's say the total charge is capital Q, so I can write it down as kq by root over r square plus x square. Okay, so this is my potential at a point P due to a ring of charge. Okay, so as I said, potential finding out was simple, but we can also find out the electric field for the same ring of charge. Okay, but before we end with potential, let me tell you one more thing, that this is the potential at the point P at a distance x. What happens to the potential at the center? Okay, so for the center, that means I'm taking P here. If I bring it to the center, this x will become 0, right? So therefore we can write down that potential at the axis, I write it down as axis, is nothing but this value, kq by root over r square plus x square, and the potential at the center center means x is equal to 0. So at that particular point, it would be k q divided by x is 0. So this is root over r square, this is r. Please remember these formulas, very handy. Okay, you need to solve, you want to derive, you need to use it, a lot of space. Okay, needed. So this is the potential because of a ring of charge. Okay, now let's find out the electric field because of this ring of charge. Okay, let's find out the electric field. Electric field is tricky because electric field is a vector quantity. Electric field, so electric field is a vector, very important. So the approach cannot be the same. So what I say is, I have got a ring of charge, and it has got the positive charges on the edges on the surface, and I want to find out the electric field at a point P. Okay, let's say this is my point P from the uh, it is at a distance x, and again everything remains the same. This is r, okay, and this distance is, let's say, small r. We know what is small r, okay. Small r is equal to root over of r square plus x square, okay. But now we're finding out the electric field, so let me take a very small charge here, which is nothing but dq. And we know electric field is directional. This is positive. If I want to find out what is the direction of this electric field at this point P, we can imagine a test positive charge, and we see whether it will get repelled or repelled or attracted. So it gets repelled because this is positive, test charge will be positive, so the electric field will be in this direction. Don't get confused here, because many a times you might also get a negative ring of charge, the electric field will be in the opposite direction, okay. So this is the direction of the electric field. Now you see this electric field, it's a vector, hence directional, is making an angle with the horizontal and vertical. So this would be my horizontal component, and this would be my vertical component. So if this angle is theta, this angle is also theta, vertically opposite angle. So this component is ep sine theta, and this component is, sorry, cos theta, not sine, ep cos theta, because it's adjacent to theta, and this is ep sine theta. These are my components. Now you see, this is only for this dq. I can consider another dq here. Three-dimensional picture, again it lies along the axis. I'll again get a cos theta component, but the cos theta component will be in the same direction, but the sine theta component will change its angle. It might be in this direction, okay. Because it's a 3D picture. Imagine this. Exactly in the opposite, if I take dq, I will again find out the electric field. I will see that this will be in this direction, cos will be in this, but sine will be now in this direction, ep sine theta. So if you consider a ring, and if you consider it to be a three-dimensional picture, you will see all the sine components will be opposite to each other. ep will remain the same because it is at the same distance. All the sine components will be opposite to each other, but the cos component will keep on adding up, okay. So that means it simply says that because of symmetry, we can say, because of symmetry, sine components gets cancelled. Very important to understand this. And cosine components add up, add up. The cosine component will get added up, okay. So that means if I want to find out the net electric field, I have to, this was a small electric field, I can write down it as dE, because this was because of the small charge. So if I want to find out the net electric field, I have to integrate, but then I have to integrate it along this vertical component, or sorry, horizontal component. The vertical components are getting cancelled, so I'm only adding up the horizontal component. So I can simply write it down as dE. Let me drop p here for convenience, cos of theta. So if you consider the magnitude of the electric field at any particular point, we can easily find it out, okay. That's quite simple. uh, okay, so that's it, okay. So if I want to find out what is the electric field at this point, only the magnitude, we know it is nothing but kq by r square. Q is small dq divided by distance square. So distance is this r. Let me just keep it as r only, r square. So in place of dE, I can write it down as k dq by r square cos of theta. This cos theta comes entirely because it's a scalar vector quantity. So I can take k outside, r square outside, cos theta also outside, because this theta will be constant, the angle will remain the same from the center into dq. Okay, so in simple words we can write it down as k dq is the integration is total charge. Let's say the total charge is capital Q divided by r square. What is cos theta? You can consider this triangle with theta, so it's nothing but base by hypotenuse. So I can simply write it down as x divided by r. That's my cos theta. So that means if I want to find out what is my net, it would be nothing but k q x by r cubed, but we know what is my r is by trigonometry, it's r square plus x square, so it would be nothing but kqx divided by r square plus x square root. So it is half, there is a cube there, so it would be 3 by 2. This is the electric field. Okay, very important concept. This is the net electric field. This is the net electric field on the axis. If we want to find it out at the center, we can do that as well. Okay, so the electric field at the center, that means x is equal to 0. Okay, x is equal to 0. So if you look into the electric field at the center, you put x is equal to 0, this will become r square 3 by 2 r cube, but x is 0, so this will become 0. So E at the center is 0. So this is again an important conclusion, because there is an x at the denominator, so on numerator, so it will become 0. So see, this is so interesting. The potential is not 0 at the center, but the electric field will become 0, because we know in case of hollow sphere also, even if you're considering a solid sphere, non-conducting solid sphere, sorry, a conducting solid sphere, the charges are always on the surface. The electric field will be 0 at the center. So this electric field is 0. You can prove it even by using Gauss's law. Okay, but even if you don't use the Gauss's law, from this particular formula also, it comes out magically to be 0. So that's the idea here. So whenever you're doing any kind of problem on potential, try to think about what happens to the electric field for that same system. That makes your concept clearer. One is vector approach, one is a scalar approach.